Okay, so we are recording. So welcome to the seventh session of our course, and we're talking about energy-based models today. So till now we have done VAEs, we have done diffusion models, we have done flow-based models, we have done elbow-based optimization. We have shown that we are able to compute likelihoods for a lot of generative models. It can be used to generate novel samples and so on. Today, but one thing was common till today, the common thing was we were taking a latent Z and it was causal latent, and we were learning a function f such that f of Z was equal to x, which was your data distribution. This was the commonality between all of these models. We had done variational inference, we had done flow models, a lot of things, but all of them were actually transforming a random variable Z to the probability distribution of the data. So we were converting P of Z, which is a normal distribution, which is normal or uniform or any distribution you can sample from. You can sample easily. And we were converting it into P of X, or the data distribution. This was all our goal. In a VAE, we sampled from a normal distribution. We pass it through a decoder and we got the P of Z. In a flow model as well, we sampled from the sample from a normal 0-1 distribution, and we learned a function that converted it to the data distribution. In diffusion models, we were denoising from a normal distribution to get the data distribution, right? So today we'll be moving a bit away from the idea. So I'll just write it down. VAEs, you take Z from normal 0-1, pass it through a decoder P theta, and get your data X. In diffusion models, you have your Z sampled from normal 0-1, you pass it through, you pass the noisy estimate through this epsilon theta, you denoise, and you get X. In flow models, you sample from Z from normal 0-1, and you learned a function f, or in our case, f, because we were going from Z to X, which converted directly to data distribution X. Could be F1, F2, a list of FT. So it was a composition of different functions. So on, right, all the way to F1. And it was the choice was that we could select a set of functions. And all of these were actually considering this structure where we had a latent Z and we were converting into the data distribution. So again, I reiterated the idea, but now we will do away with this idea for today's session. We will not consider the latents. Instead, we'll try to learn a generative process directly from the data. And this will be completely physics inspired and inspired from the laws of thermodynamics that low energy states are. So the inspiration is of these models is from thermodynamics. It says that low energy states are more stable. Right? So we have done this in our school that we studied Arrhenius equation, which said that when which molecules would be stable and so on. And we would see a similar model over here. Okay, so this is the inspiration that low energy states are more stable, and we would need to know if the energy of a data is low or high. So we pass a data point X through an energy function. H will be denoted in as H because E, a lot of people do it with using E, but we are going to do it with H because we don't want to mix up notation with expectation, which will also be using E. H is for the heat often used for energy. So this will give me h theta of x. If this is if this is the energy, your likelihood should be high. And often what you end up doing to convert that to energy to likelihood. So what I mean is, say you have data samples like this. So this is your energy function h theta of x. And say you have samples like this, a lot of samples over here and only one over here. So clearly these states are more likely, and being likely means low energy. More and likely means more stable. And more stable means low energy. And low energy would infer that this would be in a low energy state, whereas there'd be a dip here, and then we would have something like this. But this could be a possible energy function. Because here there's so much data that these would have low energy, then there's a high energy. There's a small dip over here because there's some data, and then you would have high energy again. This would be one of the energy functions that you could learn to explain the data. This is likely, so low energy. So let's mathematically see what does that mean. What it means is, I would say, your likelihood p theta of x, right, is proportional to e to the power of, say we will define this as minus of h theta of x. Clearly you see, if h theta of x is low, p theta is high, right? That's what we want, because there's a negative of the exponent. So we know that the e to the power x minus x function is something like this, right? So the higher the energy, the lower is the likelihood. So this is my p theta function of in terms of h theta of x. Theta of x. So if the energy, if your energy increases, your likelihoods decrease. That's what we want. So again, I'm reiterating, when we have a lot of samples from a particular in a particular region, it means that those are stable regions. And stable regions means it has to be low energy and it must be high likelihood. So you can also think of it, high likelihood means stable region, and stable region means low energy. So this is the thought process. Such more data infers high likelihood, which in turn infers more stability, which in turn infers, what do you infer? Low energy. Okay. So all we'll learn here is we will learn a model, and this will be just outputting a single scalar number. We'll see this is so powerful that it can generate images in the highest quality and give you likelihoods in the highest quality and things like that. So again, these are the advantages are likelihoods computation is trivial. Generation, at least in latent space, is good, and so on. So you can do conditional generation, and similarly, similarities can also be measured. Similarity between data can be measured, right? So you can measure the similarity between data. For example, if P of YouTube model, say P of X comma Y with a labeled data, and you say P of X dash comma Y dash, if this is low, which means that e to the power of minus H of XY minus P of H theta of X dash Y dash, right? If this function over here, can you tell me if the energy differences between these two functions is low, right? Then what can you infer? That the ratio that you have over here is similar to one another, which means that they could be from the same class. So they can be used as, you can see that similar, the data is similar between one another. So for example, say the energies are similar, so this will be close to 0 to e to the power minus 0, which is be close to 1. So this would be much, just a moment. So this would be compared to, okay, let me just think about it. Should we take the absolute value over here? So, okay. So what we should do is, if H theta of X minus H theta of X dash Y dash, right? We could pass the labels, and we would pass the labels over here. So whatever label you want to say, for example, if I'm going to do label prediction, so I will give a sample image of a cat, for example. I'll give a label cat, image of cat, and label of cat. And I'll see, I will pass an image, since we will come to this, why we would do that. And we will pass an image of the novel image. And we would pass all the labels. We would have K comparisons, if there are K classes, K labels. So we would have K comparisons, right? So if the label corresponds to the correct matching pair, so these two would be similar, right? So K labels, and correspondingly here you would also have class K. So the way of comparison is, we would take an image from, this would come from the training data. Say you would have image class K, label K. This is a novel image. And you would say pass label K, right? So what you can see is, if this image, novel image, if novel image belongs to class K, then H theta of X comma Y would be very close to H theta of X dash comma Y dash, right? Very good. So if that is the case, so they would be very similar to one another. Therefore, this difference, H theta minus H theta dash, would be near 0, right? So we would, but mod of H theta minus H theta dash would be high if not matched. So this is how you do matching or label prediction using EBM, energy-based models. And if they are very, very high, if they are not matched, right? So if say we have not yet computed how do we compute the loss functions and things like that. I'm just telling you how you can use the energy-based models and see if they're high. So e to the power of H theta minus H theta dash would be high. So instead of taking the negative value over here, you can just take the absolute value. So that will help you, because we want, and we don't even need the exponent over here. So, right? So we would not even need the exponent. So we could just take the log of these two numbers and it would get the value you intend to. So that's it. So we'll see why this ratio is more important. So if you take this is basically the mod of the log of P P or P by P dash. And this is high, which means that this is different class. Low means same class. So the minimum of log of P class K by P novel is taken. So this is what you do. You take the minimum class that minimizes the differences between the energies. That's fine. So this is how you do similarity between two measures. So generating is, we'll see how we generate. Likelihood P theta is just proportional to the e to the power minus P theta or H theta of X. Right. So this is my energy encoder. So this model would just take an image or any data that you have and would give me a single number, H theta of X, which is a scalar, right? So, and these itself is so powerful that you can do a lot of things with it. Now, you can see that just this is not a probability distribution. So it's a likelihood, has to be a probability distribution. So in that case, how would you make it a probability distribution is the question. So P theta we have seen of X is proportional to e to the power of minus H theta of X. Sorry. Minus of H theta of X, right? So now to make it a probability distribution, what would you do? Clearly you would do this, right? P theta of X is equal to the integral over all of X, because it's a function of, we're going to normalize it, because our property that we desire is integral of P theta of X over all X is equal to 1, right? So to get that, you will have to divide this by e to the power of minus H theta of X, e to the power minus H theta of X. This is just normalization. So normalization. And clearly, if you now integrate P theta of X on both sides, P theta of X over all X dx, this is e to the power minus H theta of X dx by this constant X e to the power minus H theta of X dx, which is nothing but equal to 1, which is what we desire. This is the probability distribution property of sum of probability equal to sum of total probability equal to 1. Total probability is equal to 1, right? So this is all we want to have. So let's see how would you do that. So let's do it one by one. So now we have seen that the likelihood would be low for data points where data points are clustered more, high for where there is no data. So we would like to train a model. What would this H theta model do? Say if on initializing randomly, you had an energy manifold of this form where you had more data. This is your theta 0, right? And this was your data point. So say this was one more data point. So you see that wherever data was there, you by initialization, they could have had larger energies. But as you train the model, what you want to do is you want to push this down. And since the total energy has to be conserved, so you have to push this up or pull up. So at t tends to infinity, your energy function would be something like this, right? So your energy function would be something like this. So this is theta t tends to infinity as you train the model. And how would you train the model? Let's see. So I have seen that my law, the P theta of X is equal to P theta is equal to e to the power of minus H theta of X by the integral of H theta of X dx, right? This is often known as the partition function and often denoted by Z theta. So this is often written as, if you see in the literature, there's often written as e to the theta of X by Z theta, which is a constant. It's independent of X, it's a constant. Also called the partition function. Because it actually normalizes or partitions the the data space. For every data point, it will always be normalizing by the total value of the entire data. So, but this Z theta is not tractable. The problem is the entire see today. So you would ask me why, what is this is so simple, right? Because H theta is a single model. You would just pass X here, you would get H theta of X. And you would just do gradient descent, right? T of T plus 1 is just theta T. And you are learning the model parameters and you're trying to increase the likelihood. So say gradient of log P theta of X, isn't it? That's all you will try to do, right? This is the learning rate at theta equal to theta T. Right. So this is the likelihood, because the loss, this is we are trying to maximize the likelihood. The objective is to maximize the likelihood of the model given data, right? So this is all you're going to do. But there's this problem. So again, overall data points I equal to 1 to n. If you have data, and then this is 1 by n. So if you have n data points, you just maximize the likelihoods over all the data using gradient descent. This is a gradient descent optimization. So you're needing the gradient of log of p theta of x. This is for gradient descent. You need this gradient, right? So of the likelihood gradient, for gradient descent, we need the gradient of likelihood. Now, the entire issue with this, the problem, the difficulty is this. What is the difficulty? The difficulty goes as follows, is the computation of the partition function. Partition function Z theta. And we'll see a lot of workarounds using score models and things like that, where the partition of this partition, or the computation of the partition function is very, very complicated. Why? Because you can see the Z theta of X, just do it in here, Z theta, or not of X, sorry, X1, X2, all this integral over all values of XD. And you would have e to the power of minus the vector X, H theta. The vector is x1, x2. If it's a d-dimensional vector, dx1 to d. So what I'm trying to say is your x is actually lies in some d-dimensional space. So you will have to do an integral in this r d-dimensional hypercube, and you'll have to integrate over all possible values of x. Could be between 0 and 225 and things like that. And this is non-tractable. Tractable. So that is, it's exponentially going to explode, right? Because you would have this as a dimensionality of even if it is a discrete space, even if it's a 225 dimensional space, you will have to sum over all the possible combinations, right? So for example, if you have a 222, so if you have n cross 3-dimensional image, this is your image, and each takes value between 0 and 255, right? Just think of the combinations you would need. So number of this summation would be between Z or X1 between 0 and 255, X2 between 0 and 255, and dot. So it's just like 255 into 255 dot n cross 3 times. So this is like 255 to the power of n cross 3, or n3 n squared. Can you understand the complexity of this sum? It's intractable. It's NP hard problem. If it is real numbers, you cannot even compute it. So we have to find workarounds to actually compute this. And how would you do that? Therefore, as you cannot compute the Z theta, the computation of log of P theta of X, which is equal to log of e to the power minus H theta of X by the integral of e to the power H theta of X dx is equal to minus of H theta of X minus, this is the partition function, Z theta, the gradient of log of Z theta this becomes very, very difficult, right? So you can clearly see that this is impossible to calculate. Therefore, the likelihoods gradient is impossible to calculate. Difficult for gradient of log p theta to compute. So this is the entire problem of energy-based models, and throughout the next 1.5 or 1.5 hours, we'll see how to get a workaround into computing the partition function. And once you're able to do that, you would be able to train energy-based models. So we have seen the definition of the energy-based models. Low likelihood is high, and low energy is high likelihood. We've seen the partition function, and we'll see a score as well on how many ways can you train the EBM. So we have seen the gradient. We'll see the gradient-based optimization now. And if you're asking me what is the score, so we'll come to score-based models. I'll just answer this question and tell you to keep it at the back of your head. So I have showed you log of p theta of x is equal to minus of h theta of x minus log of the z theta, right? See, Elise, this is you taking the log here. If I take log on both sides, this is what I'll get. Now, if I take the gradient with respect to x, or the partial derivative with respect to x, you can clearly see, which is the score. We have discussed this in diffusion models. The score is the derivative with respect to the input image or the input dimension. This is nothing but the derivative of the h theta of x, keeping theta constant and taking the derivative with respect to x. But this is independent of x. Right? This is independent of x because you've integrated x out completely, right? This is, you can clearly see, you can integrated x out. Integrated x out. So this goes to minus the gradient of log of z theta. This goes to 0. So I'll tell you to keep this in mind. It is just the score of the energy function or the derivative of the energy function. We'll see how is this helpful in the end of this session. So modeling the score as we did in diffusion models would be much easier for energy-based models. And that's how people train energy-based models often. It will save you a lot of cumbersome things, which let us first discuss the cumbersome things here first, because you'll see that the score modeling is much easier because of obvious reasons. Let's see the cumbersome details here first. So I've shown you what is this is my gradient descent optimization, and let us try to find out what is the gradient descent optimization. And okay. So this is also known as on doing gradient descent optimization. It often leads to what is called as a contrastive divergence. And we'll see the special case of contrastive divergence. This is first case is MLE, and MLE, the special case is contrastive divergence. So there are two methods first using gradient descent. The gradient optimizations would be gradient descent would give me two methods of training if you are energy-based model, that's maximum likelihood estimation. And the second method is contrastive divergence. So these are the two methods. Let's see how would you do that. Okay. Not a difficult thing to do. So let's get started. So, okay. So number one is maximum likelihood. And for maximum likelihood, I need the gradient of log p theta of x, right? So I would just put a tick mark on things we have done. So this is done and this would be done. And then we would see how would you do Monte Carlo estimation. Then that will be the next. But then we'll go to contrastive divergence. Okay, log p theta of x. How can I write this as? Again, this term over here, recall, is equal to e to the power minus h theta of x by the integral of e to the power of minus h theta of x dx. So I will write this as minus of h theta of x minus the gradient of or just for the time being, just slide down the log of z theta. So z theta. So this is the gradient of h theta of x minus the gradient of log of z theta. And let us just compute the closed form solution for z theta's gradient. So that is not a difficult thing to do. This is a log, so 1 by derivative of the log is 1 by z theta into the gradient of the partition function. So this is what I'll get, right? So now let us see what does this mean. H theta minus, and I'll tell you to keep this in mind as well. So we'll be needing it multiple times. I'll just put a box around this. It'll be very helpful. And let's see, what does this thing mean? Right, so this will be by z theta. This is the derivative of e to the power of minus h theta of x dx. Now you see the integral is over x. So I can take the gradient inside, right? I can do that. That's a good idea to do. So let's do that. And when I take the gradient inside, because it's an independent variable, I'll get a derivative with respect to theta inside the integral, assuming the integral exists, of course, and I'll get 1 by z theta, the integral of the derivative of this is the derivative of h theta of e to the power of minus h theta of x is, so this I'll just not write over x, I'll just put x over here. So the derivative of e to the power of minus h theta of x is minus of gradient of h theta of x, right? Into e to the power of minus, by chain rule, we take the derivative of the exponent, which is the same, and then we take the derivative of the function h theta of x, which is the argument of the exponent. So you get this integral is over the gradient of h theta, and you get a plus here. So we just put minus here just to avoid step jump. And I'll get e to the power of minus h theta of x dx. All right. So now I can take h, this is a constant. Again, I can take it, it's independent of x. So I can put it inside the integral. What I'll get is gradient of h theta of hz integral of, so minus and minus becomes plus, the gradient of h theta of x e to the power of minus h theta of x by z theta dx. And what is this? We know this is equal to the p theta of x. Wow, this is so nice. Why? Because this is now an expectation, right? So this is an expectation of h theta of x plus the expected value of x being sampled from p theta. This is the distribution over theta of x, and you have the gradient of hx. Right, so the expected value. So therefore, the expected value of gradient of log p theta of x being sampled from this is my maximum likelihood estimate. See, this term is constant and independent of x, so I'll not take the expectation over the second term. It's just going to come out of the expectation. It's just this, the expected value of x being sampled from px, the gradient of h theta of x, minus plus of the expected value of x being sampled from p theta of x, the gradient of. So I get two terms over here. So it's very, very easy now. Why? Very, very easy in terms of mathematical understanding, but implementation would be a bit difficult. We'll see why. See, so I'll get an x, I'll x from px. So I will take that from data distribution. I'll pass x through the energy-based model. I'll get h theta of x, right? Now I will pass x dash. I will sample this from p theta of x, right? When I sample this from p theta of x, what will I get? Then I'll pass, after I sample this from p theta of x, I'll pass it through this. I'll get h theta of x dash. And once I do that, I can take derivative with respect to theta and I can do gradient descent. This is the entire idea. And I'll do the back propagation, right? But the question is still, difficulty is how to sample from p theta distribution. That is a very, very big question to ask. So the answer is very simple. It's not difficult. You just do gradient descent. Gradient descent. That is, we want x that maximizes likelihood of under the data distribution. So what you do is, this is called Metropolis-adjusted Langevin Dynamics. So you do, this is basically gradient descent. So what you want to do, you say sample x from px, right? You could sample from pz as well, could sample from pz as well, but this is known to be more effective empirically, because these are already images, and going from noise to images, as you know, in diffusion model takes quite a bit of a work. And here I'll not do that work. I'll just take it from p of x, and my goal is to convert it into p theta of x. So how would I do that? So I will iterate k equal to 0 to p, t tends to infinity, as large as you can, xk plus 1, and I'm just doing gradient descent. If I'm doing gradient descent, xk plus, what is the objective? I want to maximize log of p theta of x, right? And my optimization variable is x. So I will just do gradient. This is a score function, log of p theta of x, lambda by 2. So this is just gradient descent. Gradient descent. So you're maximizing likelihood of data given a model. So, or getting the best x. So it is shown that this is step 1. This is 1. And for diversity, you add, so make it a PD or differential equation, you add lambda epsilon, and where epsilon is sampled from normal 0-1 distribution. Right? So you're going to do this, and you're going to add a small amount of noise so that you have this idea of novelty, because this function is going to be constant. This is going to be neural networks are fixed. So to have variability, diversity or variability, you add a noise, some small amounts of noise. So there are multiple advantages of doing it. You can see it in my RL course, that this makes it a PDE. Probabilistic PDE is a differential equation. This is a probabilistic differential equation where you have as a stochastic differential equation, sorry, not partial differential equation, SDE, where you have, if you take this to this other side, the differential of xt plus 1 is actually from a sample from a distribution, the differential of x, right? That's all it makes it. And it gives having the intuition, it just makes it more diverse. makes the gradient descent more diverse so that you don't end up sampling the same things again and again. So this is called Mala algorithm or the Metropolis-Hastings algorithm. So this is what you have. You sample ZK and you try to raise this. Yeah. So you could add small amounts of noise, and I think you can just have lambda and epsilon. So that's not a problem. You can also have another variable here, say alpha, and this could be close to 0. And in my, I have written this as Z and this as epsilon. So this could be close to 0. And you add very small amounts of noise. That's the idea, so that you get diversity. So that's what I've written over here. You can see. So I'm just doing gradient descent. And this is my variability term. So we start from a known distribution Px, and you do Mala, you get P theta of x. So this is for every, during training, you will have to sample from the P theta of x. So, and then over K steps or T steps. So the problem is this, it is slow. So what is the downside of this? Drawback. So this works perfectly fine. Drawback is it is slow. Very slow. K has to be as large as 100 to 1000 for convergence to P theta distribution. Right? So each step of gradient descent is like this. Sample a batch, sample 2 batches actually. Say x1, x2, compute del theta of h theta of x1. This is for term 1. From here, px to p theta, do k steps of Mala, and then using x2 dash, compute h theta of x2 dash, and your loss function, the gradient of the log p theta of x is x belongs to x1. Just writing it once again, log of, sorry, h theta x1 or x plus of x belongs to x2 or x dash belongs to x2 dash, which is after Mala. Gradient of. Okay. Now when this is an optima, sorry, I'll put a dash here. At optima, theta star, the gradient of log p theta star of x is equal to 0, which means that the gradient of h theta of x is equal to the gradient of h theta of x dash, right? At least in expectation, because that's what we are doing. We can get 1 by n, 1 by n. Sample 2 batches where n samples, right? Which means px goes to p theta. H is constant. H is the same function, right? So in distribution. In distribution, these two become same. That's why this summation goes to 0, or this derivative goes to 0, and you have at theta star, right? They are equal in distribution because the gradients you can see is going to 0. they're becoming equal, and there's just all the different, there's a difference on both sides, it's just these two functions. And only when there'll be these expectations will be same is when px equal to p theta. And clearly in distribution at theta star, we have learned the distribution of px. So the rate determining step here is the mala. For even one step of gradient descent, you need to do 1,000 steps of mala. So can I make, so the next improvement is, can I make MLE faster? So I have totally got log p theta of x as the x being sampled from px, the gradient of the energy function with the data from the data distribution plus the gradient of the energy function from the model distribution. Right, so let's put x dash to not mix up. So I want to make this faster. And to make that faster, what we will do is we'll do contrastive divergence. So contrastive divergence is an MLE method which would make this thing faster. Okay, so what we have covered now is the Mala algorithm is covered. We have covered this, the gradient and so on. And now let us see what the contrastive divergence proposes. Right? So to make it faster, drawback of MLE is we need to do a large number of steps to get p theta distribution. To fit, that's what the first point I've written in fair, to fit p theta to the data, the idea is to fit the p theta to the data, obtain maximum likelihood, we need to sample from px, and we need to keep doing it for over the Langevin dynamics. And this makes it very, very slow. And how would you make it faster? So instead of doing this contrastive divergence, we define a contrastive divergence loss, where this is the difference between the KL divergence. This is my MLE, as we have seen before, between the data distribution and the model distribution. This is basically the MLE we have seen basically before. And you have a difference between the model distribution and after running t steps of Mala. T steps of Mala. This is in session 1. We have shown that the KL divergence, minimizing the KL divergence is actually optimizing for or maximizing for the likelihood. So let's look at this first thing here, term 1. So my loss of contrastive divergence is defined as dKL of px, p theta, minus dKL of pi theta px. What does this mean? I'll just explain. But let's try to understand the first term over here. Term 1, we have seen this in the class before. So this is px log of px by p theta. So this is equal to the entropy, or the negative entropy of, again, I'll write full because I'm using h for the energy function, entropy of x, or the negative of the entropy of x, and the integral of, or the expected value of, just expanding the log of p theta of x. The negative of this. This is independent of theta. This is the likelihood. So it is, if you are minimizing this, it's maximizing. Minimizing this is maximizing this. Right? Or the likelihood. So clearly, first term is the KL divergence or the likelihood maximization term. The second term that I have over here is interesting. So you have observed that I have started from the px distribution, done the Mala algorithm, and have converted into p theta distribution, right? This is from xk plus 1 equal to xk plus lambda times gradient of log p theta of x plus epsilon zk, right? This is what I have done in the Mala algorithm. This is the Mala algorithm. This is the Mala algorithm. This is what I've been doing. And I've been trying to do gradient descent on the data. I am saying instead of completing the entire step, say I don't do all 1,000 steps of mala. Instead do for t steps. Say t could be between 5 to 10 and so on. 5, 10 and so on, right? So if I do that and I represent, so I have gone somewhere here and that I represent, say this is my k steps. This is my t steps. Pi t of px. This is what I will refine as pi t of px and sometimes as q theta. And we'll see. So this is like after t steps of MCMC. After t much less than capital T steps of MCMC. So therefore, we get this second KL divergence term that is between the data that is going towards P theta and the model distribution, right? And I say that I'm going to optimize. So this is cooked up, this equation, right? We'll show this a bit later. So now step 1 is to show that the DKL of Px P theta is greater than equal to DKL of pi t of Px P theta. If you can show that and equality holds for P t equal to capital T, where x pi capital T of x is equal to P theta. No, sorry, I'm sorry. An equality holds for P theta equal to Px. Right? Px is equal to P theta when you get the equality, right? So let us see why that equality holds. The equality checking is very simple. DKL, the left hand side becomes P theta, and the right hand side becomes pi t of P theta and P theta, and you're going towards P theta. Therefore, it's going to stay in P theta, again P theta, DKL, and this is 0. This is also 0. So this we are clearly seeing that at Px goes to P theta, or rather than P theta goes to Px. So you're learning the model distribution correctly. Your contrastive divergence term becomes, what does it become? It becomes equal to 0. Right? This is my optimal point when P theta is, or P theta star is equal to Px. And not at a particular initial instance. So this is exact model, which is exactly learning the data distribution. In that case, the difference between the KL divergences is minimal, right? But let us see why is it always. So I have to show that the gradient is always the contrastive divergence is lemma 2. This contrastive divergence is always greater than 0. So why is it true? So now you say you can prove it very simply. So the Langevin dynamics can be shown to, so between this is distribution Px and this is my distribution P theta, and I'm going from here towards P theta. Say I have gone pi t steps of Px. So it is known that the distribution, so since you are going towards P theta, the distance between this is my KL divergence, DKL between Px, P theta, is clearly greater than you're going towards DKL of pi t and P theta. Clearly, as we are moving towards P theta from Px. MCMC always guarantees that we move in the correct direction. So if you're moving in the correct direction, the distribution's difference is always going to decrease. Always going to decrease over t. So now clearly, if that is the case, the difference between dkl1 minus dkl2 is always greater than 0, hence proved. Right? This is 1, this is 2. So what we have shown is, so I'll come to score-based formulation here, but let's continue contrastive divergence. Continued. So I've shown now that the contrastive divergence loss is greater than equal to 0, which is equal to dkl of px p theta minus the dkl of pi t of px and p theta. So again, recall, I'll keep this image always in mind. This is D1, and this is not D1. This is my D1, DKL1, and this is DKL2. I've shown that this is greater than 0. And if Px or P theta equal to Px, then LCD equal to 0, minimized. So this loss has an optima only when the model distribution has converged to data distribution. That's all we want. That is the desired optima. This is our desired optima. And the second thing that we have is the desired optima is correct. And the second thing that I have is that the desired optima is correct. And we do not need to do all the steps of Wala. Right, where t is much less than t. So let's try and see what this loss function is. So your theta t plus 1 is going to be theta t minus, because it's a loss term, not a maximization or likelihood term. So we got to do gradient descent, the gradient of LCT. And now that's the computation that we'll be doing. How do you compute the gradient of the contrastive divergence term? Let's try and compute the contrastive divergence term. So let us do term 1, dkl. We'll do it very nicely, so that because there will be a lot of terms and we'll have to keep track of them. So I will just represent each of these terms carefully. So this is term 1. So I'll just write down which is term 1. This is term 1. This is term 2 without the negative sign. Okay. So the dkl of p theta, and I'm going to take the gradient of this. So the gradient of LC theta is theta of dkl1 minus the gradient of dkl2. So I have to take the gradient of both of these terms and show you that how it actually prevents us from doing a lot of computations. So let's do that. Okay. dkl of p theta, px and p theta is here. Just a moment. Yeah. So again, if I have to get the expansion of this term, I've already shown this. This is plus C, that is the entropy term, the negative of Px log of P theta of x, isn't it? Because again, this is where I showed it. I'll just show you where I showed it. There you go. So this, as in the first session of our course, we showed that if I distribute the log terms, so I will end up having an entropy term which is independent of theta, that is Px log of Px, independent of theta, which is, if you take a derivative, will go to 0. And you have this gradient with respect to the of a Px P theta term, which is the likelihood term. So that's all we will be writing. Let's write it down. So this is what I am having. Right? This is the likelihood term that I have, and this is the expected value with respect to x. Okay. So now if I take now it is gradient, so this constant also disappears. I just have the gradient with respect to this. And again, it's an integral over x, so I can take the gradient inside. So I can write this as minus Px, the gradient of log of P theta of x. I think we have already done this. What is the gradient of log P theta of x? Calculated it multiple times now. Where is it? Where is it? Yeah, there you go. So the gradient is just the maximum likelihood estimation, right? The gradient of P theta of x is just the gradient of h theta and the data being sampled from this distribution of P theta. And this is we have shown this. Right? This is a reason I'm copying it, because you'll be able to connect. So this is the gradient that we have already computed, and I'll just paste it over here. So I'll be able to write this as the negative of Px, and I'll just put this. Right? So this is my term. Right? DKL dx. So now what does this mean? So you have this expected value, negative becomes positive, of x being sampled from data, and you have the gradient of h theta of x, right? And this is a constant. So you don't need to take an expectation over x. So Px, the integral of Px goes to 1, and you have a negative of the expected value of x sampled from P theta of x, the gradient of this constant with respect to x, h theta of x. Okay. So this is, again, the DKL term, as I said, is the maximum likelihood term. And therefore, the maximum likelihood term is exactly going to be the same as before, right? Exactly same as before. With a negative sign, of course, with a negative sign. Right? So that's great. So now what I'll do is I will compute the second term. Term 1 was easy to compute, and I computed it very, very simply because it was already done before. The term 2 that I have is the gradient with respect to the DKL pi t px with respect to p theta. Okay, this is my second term, and let us compute this. Okay, how do I compute this? This is a bit cumbersome to write down the gradients of pi t of theta every time. So what I'll do is, again, this is a function of theta, remember, because we're going to do Mala using gradient. We're going to do Mala, and that depends on the model parameters. So it depends on the model parameters. So I will write this as, let us write this as q theta of x. Okay, q theta. So let's take the derivative or the gradient here. And I'll have q theta of x log q theta of x and p theta of x. Okay, so let us first expand the integral out. So I'll have this integral expanded to the gradient of q theta of x log q theta. Just put an equation number one here. Q theta of x dx minus of the integral of q theta of x log of p theta of x dx. Right? This is very simple. Now, once I do that, I can do the gradient, take the gradient inside. Again, these are integrals over x. So assuming the integrals exist, I can always take the gradient inside the integral and compute the gradients first and then take the integral later. So by UV rule, I can split this derivative into two parts. Qx log of q theta of x dx plus of q theta of x 1 by q theta of x. I'm taking the second term's derivative now. This was the first term's derivative. This is the second term's derivative. The gradient of q theta of x. That's right. This gets cancelled. Very nice. So now, and the second term, this becomes q theta of the gradient of q theta of x log of p theta of x plus or other UV rule. So this is the derivative of this, and the derivative of this is going to be this, where q by p theta of x, the gradient of p theta of x. Okay, this is all I'm going to have. Right? So let us see which terms can I club together and which terms I cannot club together. So I can club together three of these terms, right? Let us see which three of the terms can I club together. I can club together this term. This has a gradient with respect to q theta. This has a gradient with respect to q theta. And this has a gradient with respect to q theta. So I'll club these these three terms. And I'll write this as the gradient with respect to q theta of x. This is just 1. So 1 plus log of q theta of x by p theta of x. This is my term 1. This is what I can write this as. And I'll have a second term, which is q theta of x by p theta of x, the gradient of p theta of x dx. See, this is now very simple, right? So as soon as I do this, I can write this. This term over here has already been calculated. So ddx or 1 by f dash is known as d of, or df dx we know is equal to ddx of log of f, right? So because by chain rule, you'll take the derivative of log, which is 1 by f, and then you'll take the derivative of f itself. So I can club these two terms together, and I can write this as, I'll copy the first term, 1 plus log of, I'll just q theta of x minus log of p theta of x dx minus the integral of q theta of x, the gradient of, with respect to theta, log of p theta of x dx, right? So the second term again becomes very, very simple, isn't it? Because the second term, what is the second term? Again, I know the derivative with respect to theta. This is already known to me. I have already copied it here, this term. So if I just can copy it back over here, just put it over here, the negative of the expected value of q theta of x, because this is an integral by lotus, I can just take the integral of the expected value of x, the gradient of log p theta of x, and which is equal to, I can just I can paste the function that we have already copied. This function has already been calculated multiple times by us. This is going to be this function, right? this function. And as soon as I do that, again, this is independent of x. So I can write this as a positive of q theta, or x dash sampled from q theta, the gradient of h theta of x minus the expected value of x being sampled from p theta, the gradient of, or x double dash being sampled from gradient of h double dash. Right? So this is from, so if you're forgetting, this is from my phi t of px distribution. So where t is only a few steps. So I still have this term over here, which is from p theta, but I'll show you that this term will disappear because of the presence of the first term. So let's see. Once I'm able to do that, so let's now look at this term over here. So this term over here can be written as, what can you write this as? See, this term, I can write this as, if I take a derivative, so just one moment. Yeah. So this is the gradient of q theta of x plus the gradient of q theta of x log of q theta of x minus the gradient of q theta of x log of p theta of x dx. Right, as soon as you do that, can you see one thing that is coming up? This term over here that I have over here can be written in terms of the derivative with respect to the dq function. So I'll show you why. Let's look at that. Rather, I don't even need to expand it. Sorry for that. Let's look at this function. That this function exists. Let us consider this function for the time being. This function itself. Right? And this function, let us write this function as q theta, or the derivative of, with respect to q theta, right, of q theta of x log of q theta of x. Can I do that? So this function, this value over here, we know 1 plus log x, right? The derivative is nothing but the derivative of ddx of x log x, right? This is because this is x into 1 by x plus ddx dx log x, which is equal to 1 plus log x, right? So I will do a trick over here. I will club these two terms and I will write this as ddx, or ddq theta, or the partial derivative with respect to q of q theta of x log q theta of x, right? Since this is true, correct? And I will write this as minus ddq of q theta p theta of x. See, this term is independent of q. So I can put a constant in terms of q theta also. So wow, now this equation clearly becomes the integral of dkl, or rather I'll not come to dkl directly. So I can take the derivative dq theta of d theta of x log of q theta of x by p theta of x dx. Okay, I can do that. And now as soon as I do that, see, these are derivatives with respect to theta. I can pull this out of the integral because it's an integral over x. And I can say that this is the gradient with respect to our dd theta, dq theta of x d theta
into dq theta, the dkl, or the integral. This is nothing but the integral of q theta of x log of q theta of x by p theta of x dx, which is nothing but the KL divergence between q theta and p theta. So now I have term 2 as well. So dkl, the derivative of q theta, which is equal to pi t of px and q theta, can be written as dq theta. So again, I'll just not write this in this way because it is a negative here. So I'll write the positive term first. So dLCD, the derivative of LCD is the derivative of dkl px p theta minus the dkl q theta, which is t steps towards qpx and p theta. Right? So this will become, so the term 1, as we have found out from this is, let's say this is equation 2. So from equation 1, I can write the gradient of dkl, just recopying the equations. P theta is the expected value of x from px. Sorry. The gradient with h theta of x minus of the gradient of x being sampled from p theta distribution, theta of x. Okay. This is one term that I get. I can put double dash for the time. Okay. So now the other term, dkl of q theta and p theta, is nothing but, we have found out is dq d theta dkl q theta qx dq theta plus the expected value of x dash being sampled from q theta, the gradient of h theta dash minus the expected value of x being sampled from p theta distribution, the gradient with respect to x of h theta dash. Just copy the two terms and now I subtract these two. Subtract. So LCD becomes equal to, when I subtract these, I would cut these terms out and I will get, is there a negative sign over here? Q theta let's check the negative sign if there is any. Don't think so. Minus q theta. This is fine. This is also fine. I think this is fine. Yeah. Correct. Yeah. So I can write this as minus of dqx d theta dkl of x plus of x being sampled from px, gradient of h theta of x, minus x being sampled from pi t of px, which is equal to q theta of gradient of h theta of x dash. See, now we have the same equation. This was my MLE. But now instead of p theta, I have q theta, which has t less than much lesser steps than capital T. So which fastens the process a lot. And empirically, this is shown to be small. And therefore, we do not add that term in the loss because it's difficult to compute. Some papers do add it, but yeah, they don't make a lot of difference. To add this term, you have to just, what you have to do is you have to compute. We already know p theta of x. We know q theta of x. This term requires q theta or p theta. So for this term, you may have to calculate p theta, have to bin p theta and find the KL divergence. So there's no other way of doing that. So what you have to do is maybe for a batch, you'll have to find the distribution of p theta for a batch, q theta for a batch, and then calculate the KL divergence. So that is the issue that you have. And therefore, often this term is thrown out. It's not used to do the optimization. And this is because it makes it cumbersome again. And it is shown that this term is empirically shown to be very, very small and doesn't really affect the inference process or the training process of the model, right? It doesn't really affect the training process of the model because and it's shown empirically. But if it did not, then contrastive divergence, it would not have worked. So it's double derivative. I think Hessian's is small. Product of derivatives is in turn smaller. So yeah. So this is my gradient of the contrastive divergence. So that's how you train a contrastive divergence model. And we showed that MLE can be optimized. And we have, see, MLE was there and MLE was made better by using contrastive divergence because we were able to do away with all the sampling process over all the steps of Mala, and we could reduce the sampling to only a few steps. The final idea is score matching based energy model. And this is very simple because we have already done score matching in diffusion models. And by score matching, I mean, we will try to match the score of the model. Why do we want to match the score of the model? Score matching helps in removing the complexity of computing the partition function. The entire complexity of computing the partition function is lost. So as you have seen a bit before that when we computed the score, the entire thing, the partition function disappeared. So again, the gradient of the log of p theta of x with respect to x, this is called the score s theta of x, right? Or not, yeah, s theta of x can be just computed. Just look at this term. This is so easy. This is log of e to the power minus h theta of x minus the log of the partition function, which is independent of x. Because we have already z theta is computed by integrating x out. So this becomes minus of the h theta of x with respect to x, right? And this goes to 0. So I'm saying that the score function that I have should model the energy function, the gradient of the energy function, right? So instead, what we tell is, so this is the score, we showed the score. Now I'm saying instead of doing all this cumbersome process, match at the score level. Instead of maximizing likelihoods, match the scores. Scores, because at this level, we don't have to do much. So what we will do is we will say that the Freshett's, the Fisher's divergence, this is defined as the Fisher divergence, again, Fisher divergence is, so we are trying to model the score. Again, the score, what is the dimension of the score? So if you want to try to model the score, this is in RD, right? RD dimensional space, because H theta is in R, and you're taking a derivative with respect to X, which is in D dimensional space. So we will do dH theta dx1, dH theta dx2, all the way to dH theta dxd. So this is a d-dimensional vector. So we're going to match this d-dimensional vector with the actual score. The Freshett's inception distance says that, or the not inception, that we'll do in GAN. Sorry for that. Fisher's divergence says that we will compute the Fisher's divergence between the score, model score, and the actual score, as half isn't it? This is fine. We will say that we are going to minimize the MSE loss between the score, actual score, MSE between actual and model score. Right. So this is very, very simple. And let us do it for, let's see what happens. And we'll show it for a 1D case, and it becomes very similar for the ND case. So let X belong in R, and therefore the score becomes, the Fisher divergence becomes, so the model theta t plus 1 is in gradient descent is minus eta times d Fisher, or Fisher's divergence dx. That's all we need to do. Sorry, d theta. Right. So let's compute the Fisher's divergence and see what this is actually going to give me. So Fisher's divergence is given by half times the expected value for, if X is in R, 1D analog, X from Bx is theta of X. This is also in R, ddx of log of Bx, right? Squared. As I write that, I can write this as half times the expected value of S theta of X squared, right? S theta of X squared minus the expected value of S theta ddx of log Bx, right? And I can write the third term as the expected value of ddx of log of Bx squared, right? So this is independent of theta. So this is equivalent to optimizing for the first two terms. So this is constant plus C. So the constant is independent of theta. I can write this as the expected value of S theta squared, X being sampled from Px, minus the integral of S theta of X ddx of Px log Px dx. So let us try and compute the second term, right? The second term is quite simple again. So what is it? The second term says that integral of S theta of X 1 by Px ddx of Px, I'm writing t2 times Px dx. Isn't it? This is my second term. And as soon as I write this, I can write this as, so this is one function, and this is the other, where they have S theta. Yeah, I think this is correct. Okay, as soon as I get this, can I do something about it? So the idea is, can I do something about taking the derivative? So you see, I can have two functions over here. One function as s theta of x, and the other function of in terms of log of this function, right? So let's see how can I write this down as. So I'm just wondering, did I write this correctly? 2 times s theta into ddx of this. So, yeah, I think I did it correctly itself. So let's write this down. From x belongs to minus infinity to infinity. What I can do is you have this function and you have this function. Two functions. I can integrate one and differentiate the other. So as we know, this is the integration by parts. Integrate by parts. Right? So which one should I integrate and which one should I differentiate? So instead of writing this entire derivative, I'll just keep it in the log term for the time being. It will be helpful to calculate ddx of log of px. So integrate by parts. I will differentiate this. I will integrate this. Let's try and integrate it. Okay. So let us integrate this. So as soon as I integrate this, I will have s theta, the integral of d of log of px dx, right? Dx and dx gets cancelled. So this is going to be s theta of log px from minus infinity to infinity. So this is the boundary condition, and you have the negative term. The second term is the derivative of s theta of x, the integral of the second term, which becomes d log of ddx of log of px dx, right? That's what it becomes. So this term over here at the boundary, this is at the boundary conditions. So score s theta at minus infinity and s theta at infinity is going to be 0 because data don't exist there. So we're going to put this to the boundary condition. I will say that this is not going to exist because even the p theta term is not going to exist. S theta score at minus infinity is 0 and px is also not defined. So log of log would not be defined. So the integral won't be defined. If s theta is equal to 0. If not, if theta equal to 0. So s theta has to be equal to 0 to make it defined, the integral defined. So s of minus infinity is equal to s theta of infinity is equal to 0. So score function has to be 0 at the boundary. This is the boundary condition. Okay. So now the second term that I have over here, I'm integrating this function that I have over here. I'm integrating this. So once I integrate that, what do I get? I get log of px, right? Log of px, the great derivative of s theta x dx, right? So if I write that, okay, does that make my computation easier or more difficult? What I want is I want this to be in terms of px. So if I want it in terms of px, oh, I think I missed a trick over here. Okay, so this is fine, but this is not in terms of px. So that makes it a bit difficult to compute. So this you cannot write it in terms of expectation. This is way one. So this does not give me the results, not the right result. So instead, what I'll do is I will do an alternative way to the alternative method. So this is how you do integrals. You really don't have the exact form always. So you have to see which one is going to help you. So s theta of x, I know the derivative of this function is going to be 1 by px, which I was doing initially, dd dpx dx into dx. Right. So what I'll do is I know that this is equal to dpx. So this is canceling dx is not correct, but I can write this integral as s theta of x 1 by px dpx. And if I do that, I'll do the same integration by parts. S theta by px into px, right? Because I'll be integrating s theta of px into dpx minus derivative of, again, remember the derivative is with respect to which function? The derivative is with respect to x. So s theta of x px, right? Into the integral that is px. I think I missed a px term somewhere. Yes, I did. Sorry for the confusion. This is all incorrect. Very sorry. I missed a term and yeah. Sorry, very sorry. This is just for missing one term. Our derivatives have not been computed correctly. Sorry. Just erase this out and I'll redo this. Again, this is not the integral, right? This is the expected value. And I missed the px term over here. Sorry, very sorry. This is the expected, this is just this term, right? So the expected value of sx, s theta of x ddx of log of px is the integral of px s theta of x ddx of px, isn't it? So I didn't put this, the PDF term before, therefore we were having a lot of confusion. So this becomes px s theta of x 1 by px ddx of px dx. So as soon as I do that, I will have integral of s theta of x dpx. So this also gets cancelled for the simplicity purposes, and I'll get s theta px from minus infinity to infinity. Clearly, s theta of minus infinity would be 0, and s theta infinity also equal to 0. The boundary conditions px is equal to 0 and px is equal to minus infinity. The PDFs must be bounded, so therefore their boundary conditions are 0 minus the integral that is px and the derivative of s theta of x. This is exactly what I was looking for, and therefore we get it is equal to this term goes to 0. This is equal to minus of the expected value of the gradient with respect to theta of the score function, right? X sampled from px. So what is my the df? So df s theta and ddx of px or log px is, we have seen there's two terms, this term, and there's a negative term here. So this is negative, so negative. So I'm computing it without the negative. So this becomes half times the expected value of s being sampled from px, s theta of x squared, minus of expected value x being sampled from x, s theta of x, the gradient. So this becomes half times the expected value of x being sampled from px, s theta of x squared, minus the expected value of S theta of x. So this is for one value. This is for one dimension. For all the dimensions, you would just do, if it is x is in R dimension or D dimension, multivariate analog. So df of S theta of x, which is again belonging to the R D dimensional space. The derivative would now become a gradient log px. This can be written as, see, the square is a single number. Two numbers would have, as you can clearly understand, this will be an L2 norm. This theta of x squared, because the square in R1D is the L2 norm in ND, plus this gradient would be computed for all the terms of x. So this is so it will be for all the terms in x, you compute this. So this is defined as a trace of the gradient of S theta of x. So again, remember S theta of x is again RD. So you will have S theta x1 and you will D theta 1. Rather, it is a derivative with respect to x, isn't it? Sorry, this is a derivative with respect to x. I wrote it again in a mistake. Right? So this is a derivative with respect to x, not theta, because that's how we integrated the rate. So this is x, right? So dx1, right? And then S theta x of 1 by dxd and S theta of x t dxt. So I'm just going to add these terms. These terms is what has been computed here. So I'll just take the summation of all the terms, that is ds theta. What is the derivative of the, so this is known as the Hessian. So this will give me a Hessian. The second derivative is of a vector with respect to a vector is going to be a matrix. It's a D cross D matrix because S theta is in D-dimensional space. The gradient and x is also in D-dimensional space, and that's why we got S theta in D-dimensional space. So again, score matching, df of S theta of x is in D-dimensional space. So S theta, which models gradient of H theta of x, or minus of the gradient of H theta of x, which is a D-dimensional vector, because d scalar by drd is nothing but, as I showed, is 1 to all the way df by dx1 all the way to dh by dxt. This is the h, right? So this is in rd, and the gradient with respect to log p theta of x can be written as the expected value of x being sampled from the data distribution S theta of x squared, an L2 norm of S theta squared, plus the expected value of x being sampled from px, the trace of the S theta of x. So again, this function is in Rd. This is a D-dimensional vector. Therefore, gradient of x with respect to st is nothing but dx1 x1 ds theta 2, or rather 1 x2 all the way to d s theta d dxt ds theta 2 dx1 ds theta 2 dx2 all the way to ds theta d dxt. D cross D matrix, and the trace of this is just going to consider these terms because we showed in the integral, there's just going to be the integrals over all the corresponding x's. The others won't matter. So now, once you have these terms, you have to compute this Hessian of the score matrix. Score you'll directly get from the, so score matching will, what it will do is you will pass x S theta, right? Which is in RD, and this will give you a S theta of X, which is in RD as well, right? So as you get directly the RD matrix, you can take the RD's derivative with respect to X. And now in optimization, you can do theta t plus 1 as theta t minus. So it's since it's a loss, you're minimizing with respect to d df. So I will take the derivative with respect to this term. The second term is a bit computationally intensive. Computationally intensive. But okay, the first term is very simple. That's the idea. Here as well, you can use a unit because it's a score at the end of the day, right? Okay, this is how you do score matching. So now why is score matching is important? Because once you have learned the score, you can easily sample from the distribution x from p theta by using Mala. Because xk plus 1 is equal to xk, this is why score is very, very useful. Lambda times the gradient with respect to x, log of px, p theta of x. This then exactly is your S theta model, right? You'll just exactly like your diffusion model. You just put the diffusion model's S theta over here or something like that, whichever is matching score, and you will have epsilon times z. This is exactly what you do. And see, every time you pass the new model, you sample from z from normal 0, 1 during inference, because all of these would be like sampling from any distribution. I told you when you sample from px and go to p theta, you can also sample from pz and Mala will take you to p theta. And then you will just take the score and then you'll update this function. And people often do it in the latent space, but because it's very high dimensional space, you need a lot of compute. So what does it mean? You have an image, say you have a 512 cross 512 image. You will learn an autoencoder. You could learn a VAE as well, which is say converted into a 100-dimensional latent. And then you learn your EBM or your diffusion model. And then you use the decoder to get the 512. So this will give you 100-dimensional new data, and this will give you 500 but 500 plus 3. So these are called latent diffusion models. That's or latent ABNs. So you will do a thing which will reconstruct highly, and you'll have those high 100-dimensional space and train the EBM on that latent space, and then use a decoder to convert those latent space back into the image space. So with that, we come to the end of energy-based models as well, and which using score matching, we showed that inference is very easy, and we learned Metropolis has we learned MLE basis methods of learning it, as well as contrastive divergence methods of learning it. And so and we saw the usefulness of scores. So with that, I'll end today's session. I'll stop recording. If you have any questions, please feel free to ask them in the channel. And we'll also, from the next session, what I'll do is I'll start with adversarial neural networks or adversarial generative neural networks or GANs. And for the next 2 sessions, I'll show you how GANs are different from learning a variational inference. So we have been able to do energy-based models, variational models, diffusion models, as well as flow models. These are 4 modules in our course. And the 5th module will be doing adversarial models. And finally, we'll see if we can end recognition models can be done at the end. So with that, I'll come to the end of today's session. Thank you for your attention.